Alright, so today I'm gonna be explaining this important paper with the title Invariant and Equivariant Graph Networks. This clear paper in 2019 by Israel. Invariant and equivariant networks have been successfully used for learning images, sets, point clouds, and graphs. A basic challenge in developing such network is finding the maximal collection of invariant and equivariant linear layers. Although this question is answered for first three examples, the full characteristics of invariant and equivariant linear layers for graph is not known. So in this paper we provide a characterization of all permutation invariant and equivariant linear layers for graph data, even hypergraph data, and show that their dimension in case of edge value graph data is 2 and 15 respectively. More generally, for graph data defined on k-tuple of nodes, the dimension is the case and 2k Bell numbers. Orthogonal bases for the layers are computed, including generalization to multi-graph data. The constant number of basis elements and their characterization allow successfully applying the networks to different size graphs. But what is a Bell number? The Bell number in B sub n is the number of partitions of size n. A partition of a set is defined as a family of non-empty pairwise disjoint subsets of S whose union is S. So we consider the problem of graph learning, namely finding the functional relationship between input graphs and corresponding targets. As graphs are common data representations, this task received quite a bit of recent attention in machine learning. So the order of the tensor, the number of indices used to represent its elements, indicates a type of data. First order represents node values, second values, edge values, and so on. So the task at hand is constructing a functional relation where F is a neural network if TL is equal to L, is T. So if T is equal to T sub L is a single output response, then it's natural to ask that F is order invariant. So it should produce the same output regardless of node numbering used to encode A. For example, if we represent the graph using adjacency matrix, then for an arbitrary permutation matrix, an arbitrary adjacent matrix, the function f is order invariant if it satisfies f of p transpose a p should be equal to f of a. So if the target specify output response in the form of tensor, then it is natural to ask if f is ordering equivariant. That is, f commutes with the renumbering of nodes, operator acting on tensors. Here, for example, is the full basis of equivariant linear layers for edge data. The purely linear 15 basis elements are represented by matrices. So every permutation matrix P, the function is equivariant if and only if f of p transpose AP is equal to p transpose f of AP. So for invariant, we had this relation. For equivariant, we have this relation. To define invariance and equivariance for functions acting on general tensors, we use reordering operator, which is defined by the tensor that results from renumbering the nodes according to permutation defined by P. So it is shown that the linear space of invariant linear operators is of dimension 1, containing essentially only the sum operator. The space of equivariant linear operators is of dimension 2. The global equivariant tensor was partially treated in this reference, where the authors make observations the set of standard tensors operators, product, element-wise product, summation, and contraction are all equivariant, and due to linearity, the same applies to their linear combinations. So we provide a full characterization of permutation invariant and equivariant linear layers for general tensor input and output data. We show that the space of invariant linear layers is of dimension B of K. The B is just the Bell number, K's Bell number. So in experiments, they showed that they concentrated on possibly the most popular instantiation of graph learning, namely that of a single node set and edge valued data. For example, with adjacency matrices. They created simple networks by composing the invariant or equivariant linear layers in standard ways and tested the networks in learning invariant and equivariant graph functions by comparing identical networks with our basis, the basis of this Hartford paper, and show we can learn graph functions like trace, diagonal, and maximal singular value. So the basis in this reference, tailored to the multi-set setting, cannot learn these functions, demonstrating it is not maximal in the graph learning because of the, for example, multi-set, if you have multi-set with repetitions. So this L is this linear operator for equivariant layer. We consider a general linear operator and corresponding matrix L. Equivariance of L is now equivariant to this P transpose AP should remain P transpose L of vector of A than P. So from this equation 2, we see that finding invariant and equivariant linear layers for order 2 tensor data over one node set requires finding fixed points of permutation matrix group represented by Kronecker powers. And then they had the theoretical analysis with their proof of theorems. So they compared to other baselines on synthetic experiments. So these are the invariants like trace, maximum singular value, diagonal extraction, symmetric projection. And their graph classification results. For example, they compare different methods. For example, WL with their method. You see, it's almost the same. Little improvement. For example, for protein data set.